What if the true shape of our planet was calculated more than 2,000 years ago, with nothing more than sunlight, shadows, and courage to question the obvious? Stay with me, because once you understand how they did it, you'll realize the ancient world was far more advanced than we've been taught. Don't scroll. Keep watching, because this single experiment redefined humanity's place in the cosmos. Imagine standing in the blazing heat of Egypt at noon on the summer solstice. The air is still. The sun is merciless. In the southern city of Sin, near modern-day Aswan, something extraordinary happens. At the exact moment the sun reaches its highest point, vertical objects cast no shadow. Sunlight pours straight downwards. The light strikes the earth perfectly perpendicular, as if the sky itself is aligned with the ground. Now travel north to Alexandria. At that same exact moment, a shadow appears. Not large, not dramatic, but measurable. And inside the intellectual heart of the ancient world, the legendary Library of Alexandria, a scholar notices this difference and sees something no one else had dared to quantify. His name was Eratosthenes. If this idea already fascinates you, stay locked in, because what he did next changed science forever. Eratosthenes was not a conqueror or a king. He was a librarian, a mathematician, a geographer, a thinker obsessed with measurement. At a time when philosophy often blended with mythology, he demanded numbers, precision, proof. Educated Greeks before him, including Aristotle, had argued that the earth must be spherical. Ships disappeared hull first over the horizon. During lunar eclipses, the earth cast a curved shadow on the moon. The evidence suggested roundness, but suggestion was not enough. Eratosthenes wanted scale. He learned about the phenomenon in Sin, no shadow at noon during the solstice. He knew that in Alexandria, vertical pillars still cast a measurable shadow at that same moment. If the earth were flat, both cities would experience identical shadow behavior. But they didn't. That difference meant curvature, and curvature could be calculated. On the solstice, Eratosthenes placed a vertical stick, a gnomon, in the ground in Alexandria. He carefully measured the angle between the stick and its shadow at noon. The angle was about 7.2 degrees. 7.2 degrees. It sounds insignificant, but in a circle of 360 degrees, 7.2 degrees is exactly 1/50th of the full rotation. That meant the distance between Alexandria and Sin represented 1/50th of the Earth's total circumference. All he needed now was the distance between the two cities. Through caravan measurements and estimated travel distances, he determined the span to be roughly 5,000 stadia. Multiply that by 50. The result, approximately 250,000 stadia for the Earth's circumference. Depending on the exact length of the stadium used, modern scholars estimate his result was astonishingly close to the actual circumference of about 40,075 kilometers. Let that sink in. No satellite imagery, no aircraft, no space missions, no global communication networks. Just geometry and sunlight. Pause and imagine the mindset required to achieve this. Eratosthenes had to mentally step outside the Earth. He had to imagine the planet as a sphere viewed from space, an abstraction humanity would not visually confirm until photographs from orbit thousands of years later. This was not primitive thinking. This was cosmic thinking. And it didn't happen in isolation. The observatory culture of Alexandria thrived within the intellectual framework of a library. Scholars collaborated under the broader research institution known as a Mausian. They debated astronomy, mathematics, geography, engineering. They recorded star positions. They tracked equinoxes and solstices. They refined instruments for measuring angles. This was a civilization that understood observation as power. The ancient observatory itself was not a towering dome like modern facilities. It was integrated into courtyards, rooftops, open-air platforms where sunlight and sky were visible. Stone markers indicated solstice positions. Shadow lines were engraved into pavements. Geometry was etched into architecture. Light became data. Shadow became proof. But here's the deeper brilliance. Eratosthenes assumed that the sun was far enough away that its rays striking Earth could be treated as parallel lines. That assumption was correct. It allowed him to construct a geometric model. Two cities at different latitudes, intersected by parallel solar rays, producing measurable angular differences due to Earth's curvature. This is advanced reasoning. He was applying Euclidean geometry, principles developed by mathematicians like Euclid, to planetary scale. And he was right. Now imagine the moment the calculation was complete. The scroll unrolled, the numbers written in ink, the conclusion clear. Earth is vast, spherical, measurable. Nothing out would change in Alexandria that day. The sea still shimmered. Merchants still traded. Ships still docked. But human understanding expanded invisibly, and that expansion was irreversible. The observatory's work didn't end there. Eratosthenes went on to create one of the earliest known world maps using latitude and longitude lines. He attempted to calculate distances between major cities. He estimated the tilt of Earth's axis. Later scholars built on this foundation. Claudius Ptolemy developed more advanced geographic coordinate systems. Mariners centuries later relied on spherical Earth models to navigate oceans. Even during the age of exploration, knowledge of Earth's roundness and approximate size influenced voyages. Though imperfectly interpreted, explorers like Christopher Columbus operated within a framework shaped by ancient measurements. That is a legacy of one shadow. But here is the tragedy. The intellectual engine of Alexandria did not last forever. Political instability, cultural shifts, and eventual destruction fragmented the continuity of its knowledge. Scrolls vanished. Instruments were lost. Centuries of insight became scattered across regions and languages. Imagine if every calculation, every diagram, every refined measurement had survived intact. How much sooner would global navigation have advanced? How much earlier might scientific revolutions have accelerated? Knowledge is powerful, but preservation is everything. The ancient observatory that calculated Earth's true shape stands as proof that brilliance is not modern. Innovation is not new. What we often call progress is sometimes rediscovery. Now consider this. Today, we see Earth in real time from orbit. Satellites map every contour. GPS systems calculate location within meters. Supercomputers simulate planetary climate. But the fundamental geometry behind those technologies, the spherical model, the circumference, it began with a shadow and a question. There is something profoundly humbling about that, because it means intelligence does not depend on technology alone. It depends on perspective, on the willingness to observe carefully, on the courage to ask enormous questions. What is the shape of our world? How large is it? Where are we upon it? These questions defined exploration for millennia, and they were answered accurately long before rockets pierced the sky. So the next time you step outside at noon and see your shadow stretch across the ground, remember this. That same sunlight once revealed the size of a planet, and it required no divine intervention, no prophecy, no mysticism, only curiosity. If this story expanded your understanding of the ancient world, don't stop here. Share it. Follow this journey. Because history still hides observatories, calculations, and forgotten breakthroughs that can reshape how we see civilization itself. The Earth has always been round. The real revolution was realizing we could measure it, and that revolution began when someone dared to trust a shadow. What if the Earth's true shape wasn't proven by astronauts or satellites, but by a quiet observer standing in the heat of ancient Egypt, staring at a shadow? Stay with me, because the method was so simple it feels impossible, and yet it measured an entire planet. Don't scroll. Watch closely, because this is where ancient genius breaks modern assumptions. It begins with light. In the southern Egyptian city of Sin, near present-day Aswan, there was a well known for something extraordinary. Every year, at noon on the summer solstice, sunlight would fall directly down into it. No angle, no shadow, just a perfect vertical beam illuminating the water below. That meant the sun was directly overhead. But hundreds of kilometers north, in Alexandria, something different happened at that exact same moment. A shadow appeared. Inside the intellectual powerhouse of the ancient world, the Library of Alexandria, scholars were obsessed with patterns, measurements, and celestial movements. Among them stood a man who refused to accept guesses. His name was Eratosthenes. He didn't want belief. He wanted proof. Greek thinkers before him, like Aristotle, had already argued that Earth must be spherical. They observed ships vanishing hull first over the horizon. They saw Earth's curved shadow during lunar eclipses. But these were clues, not calculations. Eratosthenes wanted numbers, and numbers require measurement. So on the solstice, at noon, he placed a vertical rod into the ground in Alexandria. He measured the angle formed between the rod and its shadow. The angle was approximately 7.2 degrees. That number changed everything, because 7.2 degrees is exactly 1/50th of a full circle. If the Earth were a sphere, and the difference in sunlight angle between Scene and Alexandria was 7.2 degrees, then the distance between those two cities represented 1/50th of Earth's total circumference. It was geometry on a planetary scale. Now he needed distance. Caravan records estimated the journey between Scene and Alexandria at about 5,000 stadia. Multiply that by 50. 250,000 stadia. That was his answer for Earth's circumference. Converted into modern measurements, depending on the stadian length used, his estimate was shockingly close to today's accepted value of roughly 40,075 kilometers. Pause. Think about what that means. No telescopes, no aircraft, no satellites, no global maps. Just sunlight, a stick, and mathematics. But here's what makes this even more powerful. Eratosthenes understood that the sun was so far away its rays could be treated as parallel lines when striking Earth. That assumption allowed him to construct a geometric model, using alternate interior angles, a concept formalized in the geometry of Euclid. This was not guesswork. This was theoretical physics before physics existed. He imagined Earth as a sphere in space, thousands of years before humanity would see its curvature from orbit. That level of abstraction is staggering. And it didn't happen in isolation. The research culture around the Library of Alexandria, especially within the broader institution known as the Mausian, fostered collaboration between astronomers, mathematicians, engineers, and philosophers. They tracked solstices, charted star positions, refined instruments, and debated cosmic structure. The observatory wasn't just a building. It was a mindset. Stone courtyards marked with alignment lines, sundials engraved into pavements, elevated platforms open to the sky, shadows traced carefully over carved surfaces. The sun became a measuring tool. Light became data. And in that moment, Earth stopped being a mystery and became measurable. Now imagine the psychological shift this caused. Before this calculation, Earth was a concept, possibly round, possibly vast. After it, Earth had a size, a boundary, a scale. You could calculate distance across oceans. You could estimate travel time between continents. You could imagine global navigation. Centuries later, astronomers like Claudius Ptolemy would refine coordinate systems using latitude and longitude grids built upon spherical Earth assumptions. Much later, during the age of exploration, navigators relied, even imperfectly, on inherited measurements of Earth's circumference. Even explorers like Christopher Columbus operated within the intellectual shadow of these ancient calculations, though he misjudged the size significantly. But here's the tragedy. The continuity of knowledge is fragile. Political instability, cultural transitions, and eventual destruction weakened the intellectual stronghold of Alexandria. Scrolls were lost, record fragmented, knowledge scattered across regions and languages. Imagine if every measurement, every astronomical record, every diagram had survived intact. How much sooner would navigation have advanced? How differently might scientific revolutions have unfolded? Progress is not a straight line. It is a chain, and chains can break. Yet the idea survived. The Earth is spherical. The Earth has a measurable circumference. The Earth can be mapped, all proven with a shadow. Today we see Earth in real time from orbit. Satellites measure its gravitational field. GPS systems triangulate position using atomic clocks. We have images of hurricanes swirling across curved horizons. But the foundation of that understanding, it began with a man who trusted geometry. There is something deeply humbling about that, because it means brilliance is not modern. Technology changes tools, not intelligence. Curiosity has always been humanity's most powerful instrument. And here's the deeper realization. On the day Eratosthenes completed his calculation, the world did not visibly change. No monument was erected instantly. No celebration echoed across empires. But human perspective expanded. And perspective is power. The ancient observatory that calculated Earth's true shape stands as proof that the past is not primitive, it is profound. The minds of antiquity were capable of conceptual leaps we still admire today. So the next time you see your shadow stretching across the ground, pause, because once, long ago, a shadow revealed the size of a planet. If this shifted how you see ancient intelligence, don't stop here. Share this story. Stay curious. Follow the journey, because history still hides discoveries that can reshape how we understand ourselves. The Earth has always been round. The real revolution was realizing we could measure it, and it started with sunlight and a question. What if the greatest proof that the Earth is round wasn't discovered from space, but from a courtyard filled with dust, stone, and silence? Stay with me, because this wasn't just a calculation. It was a moment when humanity stepped outside itself and measured its own world. Don't scroll. Focus, because this is where ancient science becomes undeniable. Long before rockets pierced the sky, before telescopes magnified distant galaxies, there was a question burning in the minds of scholars. What is the true shape of the Earth? In the thriving intellectual capital of Alexandria, under the vast Mediterranean sky, thinkers gathered inside the legendary Library of Alexandria. Scrolls lined the walls. Maps were sketched and revised. Debates echoed through marble halls. And among these scholars stood a man whose curiosity refused to settle for assumptions, Eratosthenes. He wasn't interested in philosophical agreement. He wanted measurable reality. The story begins not in Alexandria, but far to the south, in Sine, near modern-day Aswan. Travelers reported something remarkable. On the day of the summer solstice, at exactly noon, the sun shone directly down into deep wells. Vertical objects cast no shadow. The sunlight struck the ground perfectly straight. No tilt, no angle. But in Alexandria, on that same day, at that same hour, vertical pillars did cast a shadow. That difference was everything. Earlier thinkers like Aristotle had argued that Earth must be spherical. Ships disappeared hull first over the horizon. The Earth's shadow on the moon during eclipses appeared curved. But these were observational clues. Eratosthenes saw geometry. He placed a vertical rod, a simple stick, into the ground in Alexandria at noon during the solstice. He measured the angle of the shadow it cast. That angle was approximately 7.2 degrees. That tiny angle unlocked planetary scale. Why? Because 7.2 degrees is 1/50th of a full 360-degree circle. If the Earth is spherical, and the difference in solar angle between Sine and Alexandria is 7.2 degrees, then the distance separating the two cities must represent 1/50th of the Earth's total circumference. Now imagine the mental leap required. He had to visualize Earth as a sphere in space, intersected by parallel rays of sunlight. He had to assume the sun was so far away that its rays struck the Earth almost perfectly parallel, an assumption that modern physics confirms. This was not guesswork. This was cosmic geometry. The distance between Sine and Alexandria was estimated at about 5,000 stadia. Multiply that by 50. The result, 250,000 stadia for Earth's circumference. Depending on the exact measurement of a stadion, his calculation comes shockingly close to today's accepted value of approximately 40,075 kilometers. Think about that. Without satellites, without aircraft, without leaving the ground. He measured a planet, and this happened inside a civilization many today underestimate. The observatory culture of Alexandria thrived within the research institution known as a Mausian. Scholars studied mathematics, astronomy, medicine, engineering. They tracked star positions and mapped seasonal shifts. They used sundials, water clocks, and sighting instruments to refine measurements. The observatory wasn't just a tower with lenses. It was an open-sky laboratory. Stone courtyards marked with alignment lines, elevated platforms for celestial observation, shadow markers carved into pavements. Every solstice and equinox became data. Sunlight was not symbolic. It was measurable. And here's what makes this even more powerful. Eratosthenes' experiment could be replicated today with simple tools. Place two sticks at different latitudes. Measure shadow angles simultaneously. Calculate the curvature. The method still works. That's a mark of true science. His work influenced later astronomers such as Claudius Ptolemy, who developed advanced coordinate mapping systems. The idea of latitude itself depends on understanding Earth's spherical geometry. Centuries later, during the age of exploration, navigators crossing oceans relied on spherical Earth models rooted in ancient measurements. Even though explorers like Christopher Columbus miscalculated the size of the planet, the foundational belief in its roundness had already been mathematically secured. But knowledge is fragile. Political upheaval and cultural transitions eventually weakened Alexandria's intellectual dominance. Scrolls were lost. Scientific continuity fractured. The chain of preservation snapped in places. Imagine if every astronomical record, every refined calculation, every geometric diagram had survived intact. How much sooner would humanity have mastered global navigation? How differently might scientific revolutions have unfolded? Progress is not always forward. Sometimes it pauses. Sometimes it forgets. Sometimes it must rediscover. Yet the shadow experiment endured, because geometry is universal. Today, we see Earth from space, a blue sphere suspended in darkness. Satellites measure its rotation to fractions of seconds. GPS systems calculate positions using atomic clocks orbiting overhead. But the foundation of that understanding began with a simple realization: the Earth curves, and curvature can be measured. There is something deeply humbling about that. It means intelligence is not exclusive to modern technology. Ancient minds were capable of abstraction that rivaled our own. The difference lies not in capability, but in tools. On the day Eratosthenes completed his calculation, there was no dramatic celebration recorded, no monument instantly erected to commemorate the measurement of a planet. But human perspective shifted forever. Before that moment, Earth was a place. After that moment, Earth was an object with size, with boundaries, with measurable reality. And that mental shift changed navigation, geography, astronomy, exploration, everything. The ancient observatory that calculated Earth's true shape stands as proof that the past was not intellectually primitive. It was courageous enough to ask enormous questions, disciplined enough to measure carefully, bold enough to trust mathematics over myth. So next time you step outside at noon and glance at your shadow, pause. Because once, long ago, a shadow revealed the size of the world. If this story expanded your perspective, don't stop here. Share it. Keep exploring. Follow the journey into forgotten observatories and hidden breakthroughs, because history still holds moments where humanity quietly redefined itself. The Earth has always been round. The true revolution was realizing we could prove it, and it began with sunlight, geometry, and the courage to measure. What if the most powerful proof that the Earth is round was never meant to shock the world, but simply to understand it? Stay with me, because this final piece isn't just about a shadow in ancient Egypt. It's about the moment humanity realized it could measure reality itself. Don't scroll. This is where everything connects. By the time Eratosthenes completed his calculation inside the intellectual heart of the Library of Alexandria, something irreversible had happened. The Earth was no longer a mythic stage set beneath the heavens. It had dimensions. It had curvature. It had limits that could be expressed in numbers. And numbers change civilizations. But here's the deeper layer most people miss. The experiment was simple, almost deceptively simple. A vertical stick, a measured shadow, a known distance between Alexandria and seen near modern-day Aswan, a 7.2-degree angle, multiplied by 50, planetary circumference revealed. The brilliance was not in the tool. It was in the mindset. Eratosthenes understood something profound. If the Earth curves, then space itself becomes predictable. If space is predictable, it can be mapped. If it can be mapped, it can be navigated. This was not just a geographic breakthrough. It was the birth of planetary thinking. Before this, the world was experienced locally: villages, coastlines, deserts, mountains. After this, the world became global in concept. The idea that you could travel in one direction and eventually return to your starting point was no longer philosophical speculation. It was mathematical inevitability. And that idea reshaped destiny. Later scholars like Claudius Ptolemy refined coordinate systems built upon spherical geometry. Mariners navigating unknown waters trusted latitude lines that depended entirely on Earth's curvature. Even centuries later, during the age of transoceanic exploration, the assumption of a spherical Earth guided bold voyages, even when miscalculations led to unintended discoveries. All of it traces back to a shadow. But there's something even more powerful here. The ancient observatory was not defined by massive telescopes or complex machinery. It was defined by disciplined observation. Sunlight became a ruler. Geometry became a compass. The sky became a laboratory. And in that laboratory, humanity proved it could step mentally beyond its own planet. That is the real achievement. Not the number itself, but the shift in perspective. To calculate Earth's true shape, Eratosthenes had to imagine looking at the planet from outside it. He had to abstract beyond direct experience. He had to trust logic over intuition. That mental leap is the same leap that eventually allowed humans to imagine orbit, gravity, heliocentrism, and spaceflight. Every rocket launch carries the echo of that solstice measurement. And yet, history is fragile. The intellectual dominance of Alexandria declined. Scrolls were lost. Political instability fractured continuity. The flame of concentrated knowledge dimmed. The chain of preserved insight broke. Imagine if the entire body of Alexandrian science had survived uninterrupted. How much sooner might navigation, cartography, or astronomy have accelerated? How different might global history look? Progress is not automatic. It depends on preservation. And sometimes the greatest discoveries are nearly forgotten. But the shadow experiment endured because it is replicable. Anyone, anywhere, at different latitudes, can measure solar angles and calculate curvature. The method transcends culture and time. That universality is what makes it immortal. Today we see Earth from orbit. Blue oceans, swirling clouds, a curved horizon against black space. Satellites measure gravitational variations. GPS systems calculate position using atomic clocks. Supercomputers simulate climate patterns across the globe. Yet the foundation remains geometric. Parallel rays, curved surface, measured angle. The same logic holds. There is something deeply humbling about realizing that ancient minds achieved planetary measurement with minimal technology. It challenges the assumption that intelligence scales only with tools. Tools amplify thought. They do not replace it. The ancient observatory that calculated Earth's true shape stands as a monument not of stone, but of reasoning. It proves that the human mind, even in antiquity, was capable of staggering abstraction. And here's a final reflection that matters most. On the day that calculation was completed, the Earth did not grow larger. It did not shrink. It did not change physically at all. But humanity changed. We crossed an invisible threshold from believing in a world to measuring it. That shift is the essence of science. Not just observing, quantifying, not just wondering, proving. So the next time you stand beneath the sun and notice your shadow stretching across the ground, remember, that same light once revealed the size of a planet. It required no satellites, no rockets, no global networks. Just curiosity, geometry, and the courage to trust a calculation. If this journey through the ancient observatory expanded your perspective, don't let it end here. Share this story. Stay curious. Follow the path of forgotten discoveries that shaped the modern world long before modernity existed. Because history still hides observatories, still hides measurements, still hides moments when humanity quietly redefined itself. The Earth has always been round. The revolution was realizing we could measure it, and once we learned that, there was no limit to what we could calculate next. If this story reshaped how you see the ancient world, like this video, share it with someone who still thinks the past was primitive, and follow now, because the next forgotten breakthrough might be even bigger. Stay curious, because history is deeper than we've been told.